Hello everyone, I'm Bicheng, a PhD student from Shanghai Jiaotong University. In this talk, I will introduce RISC-V confidential computing for IoT devices. This work cooperates with the RISC-V Trusted Computing SIG and sPMP task group. First, let's briefly introduce the background. I believe many of you may be familiar with this figure if you attended this year's RISC-V Embedded World event. This figure is from Threat-Free Analytics, and it indicates the emerging of the IoT ecosystem. It says 50 billion IoT devices are expected to be connected to the Internet by the end of 2030. And here lists top 10 IoT security vulnerabilities and common IoT attacks. With more application scenarios of IoT, as mentioned in the last slide, there comes more concern for security. For example, IoT devices are used for security-sensitive scenarios, like face recognition, automotive devices, and so on. The fact that IoT devices often deployed in open environments with very constrained resources, like power, cost, battery consumption, etc., making IoT devices face severe security vulnerabilities. And here summarize the essential security capabilities we recommend a generic device vendor follow and implement features to ensure the device is secure. Of course, there are many device profiles from the server down to the IoT device, where there is a trade-off between devices and features that need to be considered. For example, a server designer will be willing to include encryption acceleration extensions, but an IoT manufacturer will not be willing to include them, as he is constrained by power, CMOS, cost, battery capacity, etc. Hence, this is a general recommendation only. For more details, please refer to the RISC-V platform security model specification. What we will be talking more about today is confidential computing. To isolate various code and data from each other, there are temporal and spatial isolation techniques available. Virtualization, trusted execution environment, or TEE are examples. And confidential computing is a mechanism that ensures the confidentiality and integrity protection of code and data at runtime inside a hardware TEE. Next, I want to clarify the importance of confidential computing in IoT scenarios and identify the gap between current designs and the user's security demands. Before diving into details, I'll give a brief background of confidential computing. Confidential computing is the protection of data in use by performing computation in a hardware-based trusted execution environment, also called TEE. Without confidential computing, higher privileged OS or hypervisor have full access to VM or application memory. With a compromised OS or hypervisor, the whole system is in danger. With confidential computing, secure sensitive data is in confidential side, which is isolated from non-confidential side. OS or hypervisors only manage resources, but cannot access. So an attack on OS or hypervisor will not expose application data. There are hardware-rooted attestation, memory encryption, and trusted I/O, etc. So confidentiality and integrity of memory regions are protected. In scenario like cloud computing, it is unlikely the attacker can have physical access of the server, and servers can implement various hardware features to enhance their security. For IoT devices, things are different. They are often deployed in open environment, in which the attacker can easily access and even disassemble the device. With very limited hardware resources on IoT devices, there will be no virtualization, and the processor is relatively weak. The power supply and the hardware extension are limited too. All these differences leave IoT devices more vulnerable to attacks. So, IoT needs a confidential computing architecture with low resource requirement. This chart shows different device profiles based on RISC-V. IoT devices often don't have hypervisor support. Some even don't have an MMU. This is challenging to achieve security objectives with such limited resources. This chart lists the current security feature of various platforms. As you can see, there is still a lot to be done in the RISC-V architecture. Moreover, we are filling in the blank of confidential computing for RISC-V IoT scenarios. To clarify, let's zoom in on the confidential computing of various platforms. While most platforms have proposed their TEE solutions for server and desktop, only ARM has focused on security of IoT scenarios. IoT is one of the important target markets for RISC-V. However, there is yet to be a proposal to guide the developers and the device vendors to enable IoT TEE on RISC-V. And we are not satisfied with porting architecture of other platforms. We want to make something more scalable. We aim at IoT devices without an MMU, and we propose a new reference architecture for it. Then, I'd like to give a reference architecture of the IoT TEE. Traditional IoT architecture co-locates security-sensitive and non-sensitive applications. The system is compromised if any component is attacked. With IoT TEE, the attack surface is reduced because applications are isolated into different domains without the need of a hypervisor. Moreover, communication is only allowed through standard interfaces, so attack surface is reduced. For MSU devices, the IoT OS is still responsible for managing resources. Besides, there is an optional TEE OS for launching TEE applications. In this case, the TEE OS is responsible for isolating TEE applications. And beneath the OS, a secure monitor runs in M mode to provide isolation among domains. In detail, with the TEE OS implemented, all security-sensitive applications are running in the secure domain managed by the TEE OS, and the non-secure sensitive applications are running in the normal domain atop the IoT OS. If one prefers not to implement the TEE OS, in this case, security-sensitive applications are still isolated into different domains by the security monitor. However, they will rely on the IoT OS for security for system service. As for MU or M-only devices, the basic architecture is the same, except that the OS or both OS and the applications are running in M mode with the secure monitor. In these cases, M mode isolation mechanism is required to provide isolation between components in the M mode. In RISC-V community, we have proposals like M mode isolation, lightweight TEE, confidential M mode, and so on to provide such isolation. Next, I want to give a case study with software-hardware co-design. We have proposed a RISC-V extension called sPMP. The S-mode memory protection unit, which is an alternative to MMU for IoT devices. Compared to the pig table, sPMP can provide memory isolation and protection with less hardware resource and better memory performance. It is very important that sPMP is managed by S mode. This way, the OS can still run in S mode as usual. Otherwise, a device without MMU uses an isolation mechanism like PMP, which M mode can only access, and requires the OS to run in M mode with the secure monitor. And that will cause an M mode scramble between the secure monitor and the OS. Now, with sPMP, a device without MMU can still implement MSU privileges, isolating S mode and M mode with PMP, while S mode and M mode are isolated by sPMP. Different U mode applications are isolated by sPMP as well. Here we have the encoding of sPMP regions. The sPMP can manage regions for S and U mode separately, controlled by the S bit in sPMP configure register. Set the S bit to 0 indicates a region belongs to U mode, and set the S bit to 1 indicates a region belongs to S mode. The enforce in the chart means access needs to pass the privilege check, and deny means deny. The encoding of this red region is reserved for future use. sPMP provides supervisor mode access prevention, together with the sum bit in the CSR SAPP, to prevent user data being accessed by the OS accidentally. Of course, sPMP has supervisor mode execution prevention too. Moreover, sPMP supports shared regions. You have different privileges for S and U mode, like shared read-write, shared read-only, shared read-execute, and shared execute-only. That's the sPMP extension. For more details, please refer to the specification of sPMP. Then, let's take a look at the software side. We designed Penlai, a scalable TEE system. Our work is published on OSDI 21. Penlai is a software-hardware co-designed TEE based on the current RISC-V ISA with hardware extensions like sPMP. We have M mode secure monitor and U mode TEE SDK as the software layer, supporting devices with or without MMU. For the version without MMU, we call it Penlai Mini. Please check out our website for more details, and you can also scan the QR code here. Penlai is also open source, actively developing and communicating with academic communities like OpenEuler, OpenHarmony, and so on, and industry companies like Nuclei, Trust Kernel, Huawei, and T-Head. Here is a demonstration of IoT TEE based on Penlai Mini and sPMP. We use sPMP as an alternative to the MMU, providing isolation between S and U mode and U mode applications. In M mode, we implement Penlai Mini as secure monitor, which manages resources for secure apps and provides SPI interface for S mode and the environment core interface for secure apps. The Penlai secure monitor is also responsible for managing secure apps lifecycle, like create, run, stop, resume, and destroy the secure app. In S mode, we have a TEE driver for packaging interfaces of Penlai Mini. The TEE driver enables the untrusted host kernel to interact with the secure monitor and manages secure apps via interfaces provided by the monitor. In U mode, we have a TEE lib linked to the secure app. The TEE-lib combines modified masterlibc and a secure app library. The TEE-lib can turn system calls into O calls and provides interface like IPC. Hence, Mini can support unmodified POSIX applications. We evaluate the performance of Mini. The evaluation environment is Qmule with sPMP extension. We run OpenEuler as the IoT OS. The PMP in the figure is the full-featured version designed for device with MMU, and Mini is our IoT dedicated version. We run RV8 microbenchmark inside Enclave, and the result shows that for secure memory allocation, there is no additional overhead of Mini. For Enclave creation, also no additional overhead. As you may notice, the Mini actually outperforms the full-featured version. That is because Mini optimizes the SBI interface to shorten the creation path of the enclave. For execution performance, there is still no additional overhead. And scalability is another very important feature provided by Mini. PMP only supports 16 or fewer regions, depending on implementation. Let alone you have to use one region for the OS and one for the monitor, which leaves you 14 or fewer regions for secure apps. However, Mini can support 128 isolation domains simultaneously with only 16 PMP registers, and no additional overhead is introduced. Now, let's have a summary for this talk. IoT is surely an important scenario in RISC-V and need a corresponding security solution. Security processor with TEE system can efficiently enhance the security capability of IoT devices. However, current RISC-V still lacks a TEE system for IoT devices. So, we propose sPMP, a lightweight S-mode isolation mechanism. There is an active sPMP task group in RISC-V community. The sPMP proposal is in stable state, and we have implemented sPMP in Qmule, Spike, Seal Model, and Linux as a proof of concept. We also have real-world participation of manufacturers. For example, Nuclei designed the cores with sPMP support for IoT devices. And finally, we have Mini, a software-hardware co-designed TEE to provide scalable memory protection for IoT devices. Thank you.